So good morning, everyone. So now we examine the last part of the design of fuzzy controllers, which is based on a supervisory approach. Supervisory so means that there is somebody, or in our case, it will be a procedure that allows to derive this controller that is applied to the process. So this is the scheme, the idea. So you have, in principle, the process, and from the process you can acquire all the possible measurements, y, u, or also the state, because in case you can some other signals available and accessible. So the fuzzy supervisory is supposed to, as the word supervisor means, is somebody or an entity that is able to, from the upper part of your control, is able to acquire all possible details or information from your system, and then this is highlighted here in red with this red arrow, is able to provide you like a suggestion or how to design this classical controller. So, for example, we can design a controller, again, in the form of, for example, as a linguistic description is very simple, because, for example, if the process output is height, so height, you know that they are the linguistic descriptors is one of the linguistic descriptors that are used for describing your model, and then they will be implemented as fuzzy rules, so or membership grades. So if the process output is high, so it means that the output of your process is very high. So reduce the proportional gain slightly, so you know from the behavior, so it means that you need, from your experience, you know that if the output is high, in order to stabilize a system, you need to reduce the gain, because you know that if you increase the gain, it leads to possible instability. So normally you reduce the proportional gain, or assuming that you are using like a PID controller, slightly, because you need to pay attention in order not to reduce too much the performances, and at the same time, for example, increase the derivative gain, because you know that the positive effect of the increasing of the derivative gain, because you know that the derivative part of a PID controller is always positive, because it stabilizes the system. So, but of course, these actions need to be slightly moderate. So it's why here they added some actions that, again, as linguistic descriptors, will be implemented as membership grades. And this is the case, so a supervised PD controller. There is no integral action, because maybe is not required. And we will see also in our experiments the example of an application of a controller to the inverted pendulum. So the inverted pendulum is, if you remember, the control action needs to, normally it aims to stabilize the angle of this pendulum, which is hinged on the cart, and then at the same time you need to control to follow the reference of your position of your cart, and at the same time trying to maintain vertical the pendulum. So this is, apart from the simple example, it can seem very simple, but it's something that describes the behavior of realistic robotic systems, if you can oversee this very simple case. So applied when we want to design this controller, you have here the system of the inverted pendulum, and you have a first controller that, for example, by controlling the angle, it tries to maintain the vertical line of your inverted pendulum, and then by acting on the force applied to the cart and by controlling, for example, the the speed, the velocity, or the position, you have a position controller. So in this case, you have a simpler controller because you know that the inverted pendulum could be controlled by a multivariable controller like a LQR system. LQR controller regulator can be applied to the inverted pendulum. So this is the example of a simplified control system. And this is the, just want to show you the experimental results. So you have the angle, this is you can see, or you can imagine that this is, this peaks corresponds to the fact that you are modifying the position. So you have the pendulum has some oscillation, extra oscillations here, and then it follows, but of course it's, for example, by a simple PID controller or PD controller, the control performances are very limited because the system continuously oscillates around the reference. But if you, for example, you are including a supervised controller, so it means that the gains are modified, so the gains are not constant, but are modified accordingly the working conditions of the system. So you can see that the performances are really improved. And it's why, for example, you are able to reduce the oscillations because you are reducing the gain when for example, the regulator or the cart is close to the reference position. So it means that while reducing the gain, you are also improving the stability. So the fact that the system is quite unstable or not is nearly unstable, is stable but quite close to the instability is seen here, is highlighted here by these oscillations in the, for example, in the control input, because the control input is always acting on the system, and then also the position and the angle, the pendulum is always oscillating around the vertical position. So in this case, as we will see our case, we are designing a controller in the form of Takagi-Sugeno. So instead of a model of the controller in the form of Mamdani, we are using, normally is a typical form of our controller. Is something that, if you remember, Takagi-Sugeno model is very specific because the antecedents are described by this linguistic description. So if R is low, so you have the fuzzy relation, then so the difference between Mamdani and Takagi-Sugeno is that the consequent are functions of the reference normally, or of an input. So depending on the level, for example, here of the reference, so when the reference is low, then the control input is different from the case when R is high. So also the value of the parameters of the PID is different. So it's why this supervised controller is better, has better performances with respect to a constant PID regulator. Is something that is very specific. And the final, so when, if you remember, when you compare, when you implement this control as in the form of a filter, the final signal is like an average of the outputs. If you remember how to control, how to implement as fuzzy relations these simple two rules, is an average between the outputs of the two situations, of the two rules. Of course, they are weighted depending on the membership grade, which is activated by the value of R. So it's something that is an average of your controls, and it is something that, if you remember this picture, which is describing, I'm going backward, when we saw the meaning of a fuzzy here, you have something that is very smooth. So it's a smooth combination of different linear relations. So this is the power. It's why the system, the fuzzy model is really powerful and able to describe a nonlinear model in a simplified way. So this is the idea. You should keep it in your mind as general behavior of a fuzzy system. So the output, the complete output is in this form. So if you remember the link between a fuzzy model and its polytope is a combination. So the output of the controller U is a combination of polytopes depending. So P is a polytope, which is a combination of you remember, like a rectangular in the parameter space. So it's a combination of the convolution between these two polynomials. So it's something quite complicated in an analytic way, but is very powerful because is able to control a nonlinear system. So in principle, this scheme can be thought as a combination. Those are the meaning of a fuzzy scheduling. So scheduling means that you are modifying the parameters of your controller. So you are adapting the parameters of your controller depending on the value of the inputs. So this is the way of working of your controller. So when you are speaking or you are using this description, gain scheduling means that the parameters are modified depending on the inputs. And in principle, the again scheduled controller means like a continuous is equal to different, in this case, k controllers working in parallel, and each controller is activated depending on the input. So it's something that each controller is specific for a specific working condition. So it's why a gain scheduled controller works better than a unique, just one controller, because the parameters of each controller are specific for the specific working condition. So it's something that normally works better, really much better than the simple single controller. So when you think of a fuzzy system as a input-output mapping. If you remember, the fuzzy relation corresponds to a, well, in this case, because your controller is controlling two inputs, so the error and its derivative, you have that the control input can be described by a control surface. So in one axis, you have, for example, the error. In the second axis, you have the derivative of the error, and the output is this fuzzy combination of this. This represents the single controllers. So in this case, for example, we decided to partition our inputs using two fuzzy sets. So you see very simply that the combination of 2 by 2 fuzzy sets corresponds to 4 rules, and the fuzzy combination of these local linear models, of course you are in a two-dimensional space, corresponds to this non-linear, because these they are not linear, but surfaces or planes are combined in the middle. Here you can see the combination. So when you are here is a plane, like here, like here, like here, but in the middle, so during the transition between here and here, for example, or this region to here, this region to here, you have a smooth transition. Because this is the advantage. This represents the advantage of your fuzzy model. So you have a smooth, a continuous transition between each working condition. It's something very powerful, and it represents an advantage. So we have some examples of fuzzy control or Takagi-Sugeno control. Well, it works with also for strongly nonlinear processes. Of course, the gains depends on the output. The fuzzy supervisor so is introduced for adjusting the gain of your controller, and we compare. Of course, when we will see the comparison, normally when you compare the results of your system when it's controlled by a unique, only one controller with fixed gains with respect to the controller with varying gains, is really different, the results. So an example, if you remember, at the beginning we were claiming that, for example, a PID controller was unable to stabilize this quite simple third-order continuous time equation because of the nonlinearity here. And, for example, I don't want to use this example because it's something that is only mathematics, and I prefer to apply our solutions to real processes. So it's something that is represented the fact that the nonlinear control, for example, can be the only solution that can work, for example, for your nonlinear process. And for example, in this case, it's just a suggestion. For example, when it's very simple to design a fuzzy controller by using the description, because of course, if the output is small, then the error is controlled by a gain which is small. If the output is medium, so you need to increase maybe the action of your controller. If the output is large, then use a larger control on your error. And in fact, in this case, you can see here that you have the output. For example, this is the control, and you have that, for example, the nonlinear system, when it is controlled by the linear controller, is unstable. Here you can see that the oscillation increases, and so you have an unstable process. But when you are, for example, using a PID, a simple fuzzy controller, like in this case, it is able to stabilize your nonlinear process, which is this output. So it's something that shows that your nonlinear controller works very well. So typical applications are represented, for example, in the applications, I mean, of a supervisory control, fuzzy control. Normally is used, for example, to tune the parameters. Well, it's not our case, but I know that in some applications with our colleagues, for example, Professor Mainardi used a fuzzy controller for stabilizing an automation process. So it was working very well. And it can be used for example, for improving the performance of classical control. For example, a PID controller, maybe for linear system, cannot be enough, can work. So you can think of using a fuzzy supervisory control which acts on the parameters of the PID controller. Or, for example, is a common application. These represent, for example, applications that were studied in thesis, our thesis. We have, for example, gain scheduling applied to aircraft control. When you have an airplane, you can use a gain scheduling controller for controlling your system. So this approach represents the enhancement of classical controllers, so it helps to overcome the limitations of your classical controller. It can be used also as an interface between low-level and high-level control. Of course, the negative aspect is that the analysis of, for example, the stability, if you want, as we will see later, the stability of the analysis of the stability is can be complicated, because it may require to use, for example, the Lyapunov theory. So it can be quite complicated. If you remember, the Lyapunov theory means that you should, or maybe you will see in the course of control for robotic systems, you need to find a Lyapunov function to demonstrate the stability, and in some cases can be very complicated. So normally, for the fuzzy control, the design steps are highlighted or are described as in these points. So determine the inputs and the outputs. So one of the most important tasks is the determination of the inputs and the output. Then define the membership functions. Well, in our case, membership function will be automatically derived by means of the clustering algorithm that we saw the previous lecture. Then we design the fuzzy rules. Again, the fuzzy rules will be designed by the toolbox in Simulink. And then we will complete our investigation testing for the stability and the performances of our processes, of our control And then in some cases, perhaps you need to fine tuning, but normally it's not required. So if your design is performed at your best, it means that normally you don't require a fine tuning of your controller. It's something that, of course, it depends on the steps. If you proceed exactly with the right steps, you don't need to fine tune your controller. So this is the complete view for a design of a fuzzy controller, and also its implementation. Normally, as in the design of our other controllers, normally you need the scaling of your inputs. You need, if you remember, the fuzzifier, what we call the inference engine, which is required for computing the relations, the fuzzy relations. Then you need the fuzzifier, and then the scaling again. Of course, scaling, the input scaling and the output scaling is required in the real implementation, but since we are working in simulation, normally the scaling is not required. So the scaling normally is, for example, if you remember, I don't know if you have already attended the course of technology of the control systems. From a technological point of view, of course, you need the scaling of your signals, but in our case, we don't need any scaling. So normally, from the knowledge base, so the scaling, it requires scaling factors. So a knowledge of your technology is required. And then fuzzifier and defuzzifier require the knowledge of your membership functions. And the inference engine, if you remember, requires the definition of the rules. So this is the complete view of your controller. So in our case, our controller will be represented by this module in simulation. And it will be represented by a fuzzy inference system. So it will be an object like a module with input, output. Normally is one output. So it's directly connected to your control process, and normally it can use different inputs and outputs. Normally, yes, is multiple input, but single output. And this is automatically obtained by what we will use later, the ANFIS. Adaptive Neural Fuzzy Inference System is the toolbox that will be used for the design of a fuzzy controller. So the same, to conclude, the same module will be obtained also with a neural network. So it represents an alternative. So depending on your, I don't know, your preference or if you prefer to use a neural network, use a neural network. If you prefer to use a fuzzy model, use a fuzzy model. It depends on in some cases, for example, a fuzzy model works better than a neural network. The advantage, if you remember, that in the use of a fuzzy model with respect to a neural network is that a fuzzy model is something that can be interpreted as a better interpretation than a neural network, because if you remember, we will see later, a neural network is something that is like a black box. You cannot understand anything if you look under a block of a neural network. You know, it's a connection of neurons, weights, but it doesn't say anything about the process. But if you look under the mask of a fuzzy model, because it is a representation. As with the fuzzy rules, you understand something, because to conclude, a fuzzy rule is represented by something that says something about the inputs and the output. So it can be, it suggests something about the output. Is clearer than a neural network if you look at under the meaning of a fuzzy model. Okay, we finished here.